Hello everyone, welcome to the lecture series on kinematic analysis of mechanisms using graphical methods 1. Under this, we are studying two graphical methods for kinematic analysis. First is instantaneous center method and second is relative velocity and acceleration analysis method. In today's lecture, we will study basics of circular motion and vector representations. This will be helpful while drawing velocity and acceleration polygons in relative velocity and acceleration analysis. Consider a particle in circular motion, particle traveling round the circumference of circle. Now we know that when a particle has circular motion, it will have some angular velocity which will be directed in the direction of angular displacement. Here we have shown the particle is rotating in clockwise direction, so its angular velocity will be directed in clockwise sense, that is in the direction of angular displacement. Now for every particle in circular motion there is angular velocity. We know that along with this angular velocity omega, the rotating particle has one more velocity which is linear in nature, and the direction of this linear velocity is tangential to the path of motion, that is, it is tangent to this circle, and this is true for all the instances of rotation of this particle. At all the instances of rotation, the linear velocity will be tangential to the path of motion. Now let us name this particle as particle P and the center of rotation as O. OP becomes the radius of rotation. What we have said, that linear velocity is tangential to the path of motion at all the instances of rotation. Now if it's tangential to the path of motion, obviously it will become perpendicular to the radius of rotation OP. Well, this is about the direction of linear velocity of a particle in circular motion. What about its magnitude? Magnitude of this linear velocity, which is perpendicular to the radius of rotation, is given by the product of radius of rotation and the velocity with which the particle is rotating. V equals to R into omega. Now here we will speak in terms of relative motion. P rotates about O. So what we say, velocity of P relative to O is equals to radius of rotation OP into angular velocity of P relative to O. So VPO is equals to OP into omega PO. This V, linear velocity of a particle in circular motion, is called as linear tangential velocity. Of course, it is a vector quantity whose magnitude is equals to R into omega, whose direction is perpendicular to radius of rotation at all the instances of rotation, and the vector representing this velocity is directed in the sense of omega. In this case, omega is clockwise, so this vector is coming out in towards right. So V, linear tangential velocity, magnitude R into omega, direction is perpendicular to radius of rotation, and it will point in the direction of omega. You will always remember this. Now we have seen a particle in circular motion will have two velocities, one its own angular velocity and another is linear tangential velocity. Now let us see what about the accelerations. Take a case where the particle is rotating with uniform speed, that is omega is constant. One component of acceleration is always there for a particle in circular motions. We know that that is called as centripetal or radial acceleration, whose magnitude is equals to v square upon r. V is the linear tangential velocity and r is the radius of rotation. And the direction of this acceleration is along the radius towards the center of rotation, like this. Centripetal acceleration of p relative to O, its magnitude is equals to square of linear tangential velocity of p relative to O divided by radius of rotation OP. And the direction of this acceleration is along the radius of rotation and it is directed towards the center of rotation P. So this is the only component of acceleration present when omega is constant. Let's take case 2, where the particle is rotating with non-uniform angular velocity. Omega is non-uniform. Let us suppose that omega is increasing at the rate of alpha radian per second square. But alpha is the angular acceleration. The first acceleration, which is always there, is the centripetal or radial acceleration. We have seen this, parallel to the radius of rotation towards the center of rotation. Now we are considering that omega is increasing at the rate of alpha. So alpha will point in the direction of omega, since speed will increase in the direction of motion. So alpha will act in the direction of omega, that is alpha will be clockwise. Now omega changes, so it will cause a change in this linear tangential velocity. You can see VPO equals to OP into omega PO. When omega PO will change, it will change VPO because OP is constant. Now, omega will change, it will cause change in VPO. Now VPO changes, this linear velocity changes. There must be the acceleration which will account for change in this linear tangential velocity. That acceleration is called as tangential acceleration. Magnitude of this is equals to r into alpha and its direction is perpendicular to radius of rotation. Since this acceleration has to account for change in v, change in v occurs in its own direction, so this acceleration will point in the direction of change in v. So this is tangential to the path of motion or perpendicular to radius of rotation. Tangential acceleration perpendicular to radius of rotation, and magnitude of FTPO, tangential acceleration of P relative to O, is equals to radius of rotation OP into angular acceleration of P relative to O. Take case 2, omega is still non-uniform, but now instead of increasing, we'll consider that omega is decreasing at the rate of alpha radian per second square. First acceleration is always there for circular motion, centripetal acceleration along the radius towards the center of rotation, FCPO equals to V square upon OP. Now omega is decreasing, means there is retardation, and retardation acts opposite to the direction of motion. So here alpha will point opposite to omega. And now tangential acceleration, which will be produced as the result of change in omega, acts in the direction of alpha perpendicular to r. Now alpha is in this sense, so ft will act in towards left. So it has to be in the direction of alpha, so towards left. Alpha is counterclockwise, so ft will go this way. So magnitude will remain same, only the direction will be in the sense of alpha. Take the first example where there is acceleration, speed is increasing. So we have two components of acceleration. FCPO, particle P rotating about O has two components of acceleration, centripetal component FCPO and tangential component FTPO. So total acceleration of P relative to O will be the vector sum of these two components. FPO, total acceleration of P relative to O, is equals to FCPO, centripetal component of P relative to O, plus FTPO, tangential component of P relative to O. So what you will remember now, every particle in circular motion will have one linear tangential velocity and one angular velocity, and two components of acceleration, centripetal and tangential. Let us summarize this. V equals to R into omega, linear tangential velocity is a vector quantity, so it will have magnitude as well as direction. Now if this vector changes in direction, there will be one kind of acceleration. If the vector changes in magnitude, there will be another kind of acceleration. When the direction of vector changes, the acceleration which will account for the change in direction is called as centripetal component of acceleration, which is equals to v square upon r, and its direction is along the radius of rotation towards the center of rotation. So you will remember that centripetal component or radial component of acceleration counts for change in direction of linear tangential velocity vector. You see, when the particle P rotates around the circumference of the circle, its linear velocity has to be tangential to the path of motion at all the instances. So this vector will change its direction at all the instances of rotation. And for this change in direction of vector VPO, there is centripetal acceleration HCPO. Now if the linear tangential vector changes its magnitude, change in this magnitude is accounted by the tangential component of acceleration Ft, which is equals to r into alpha. This is the component FTPO will account for change in magnitude of this velocity vector VPO. Now let us study how to represent these free vectors. VPO is a vector quantity, it's the velocity. We will represent this using a vector. We will read this vector as VPO, velocity of P relative to O, represented by this vector. Magnitude of this vector is equals to the length of vector VPO. Its direction is the orientation of this vector with respect to any one of the axes, and its sense will be in the direction of omega. Sense means the direction of arrow, whether the particle velocity is pointing downwards or up. So VPO is a vector quantity. We represent it using a vector whose length is equal to the magnitude of the quantity. Direction is given by the orientation of the vector, and the arrow will give the sense of the vector. Now how to plot this vector? Vector VPO, we have determined its direction. Its direction is perpendicular to radius of rotation OP. So this is our vector VPO perpendicular to OP. We read this vector as VPO. When we read the vector as VPO, O must be the tail of the vector and P must be the head of the vector. So VPO is represented by vector OP. So vector OP represents velocity of P relative to O. This is very important. You should never make a mistake while reading and placing the vectors. VPO, velocity of P relative to O, is represented by vector OP. O should be the tail and P the head of the vector. Now let us learn about vector addition. When the vectors are placed tail to head, so head of the vector OP is placed at the tail of vector PQ, so these vectors are to be added, or vectors to be added are placed tail to head, and the resultant will act from starting point of first vector to the end point of last vector. So you can see the signs of the vectors which are added is counterclockwise and the resultant is opposite, that is in clockwise sense. So vector OP plus vector PQ will give the resultant vector OQ. What is important? Vector placed tail to head are to be added, and vectors placed head to head or tail to tail are to be subtracted. Now placing velocity vector in vector polygon. We learn how to place the velocity vector in vector polygon for relative velocity and acceleration analysis method. First of all, we will identify the direction of this vector quantity. This is linear tangential velocity, so its direction is perpendicular to the radius of rotation OP. This is the direction of PPO perpendicular to OP. That is represented by vector OP. We have seen this in the last slide. PPO, velocity of P relative to O, is represented by vector OP. Now suppose in vector polygon, initially we have point O with us and we want to place this vector PPO at point O. How will you place this? O should be the tail of vector. So we'll place this vector VPO at point O such that O becomes the tail of vector, maintaining the direction. Okay, we will not change the orientation of the vector. VPO, O should be the tail of vector. Now instead of O, suppose we know the point P in the vector polygon, and now we'll place this vector at point P. How will you place? Look at here. P should be the head of the vector. So we'll pick up this vector and place such that P lies at the head. So this is also important. We should not make any mistake in placing the vectors in vector polygon. Now placing acceleration vectors in vector polygon. So we have two components of acceleration now, FCPO and FTPO. So suppose in vector polygon we have with us point O. Now usually centripetal or radial component of acceleration is plotted first. This is not a thumb rule, but since from velocity polygon we can determine this V, so we have magnitude and direction of all these radial accelerations with us. So it's a good practice to place the radial acceleration vectors first, and then to it we add the tangential component. Now we have point O with us in the acceleration polygon. So we'll pick up this vector FCPO and place the tail of the vector at O, because FCPO will be represented by vector OP. O will be the start point of the vector, or P will be the end point of the vector. So this is FCPO. Now to FCPO we have to add its tangential component FTPO in the given direction. The vectors to be added are always placed tail to head. We have head of vector here, so we'll place tail of FTPO at the head of FCPO so that it gets added to it. So now we have added FTPO to FCPO. Now the resultant FPO will start from the start point of first vector and end at the end point of last vector. This is the resultant FPO. So resultant acceleration of P relative to O, that is FPO, is represented by vector OP. So O should be at the tail of the resultant, and P should be at the head of the resultant. So here we get point P. So FCPO plus FTPO is FPO vector OP. Now this was when we have point O with us. Now instead of O, if we have point P in acceleration polygon, we will have to place the first vector FCPO such that P is at the head of the vector, because resultant should end at P. So FCPO is now placed in such a way that P is the end point of this vector. Now we have to add FTPO. The vectors to be added are placed tail to head. So this is FTPO. We have added FTPO to FCPO by placing the vectors tail to head. Now the resultant, we know that resultant FPO is given by vector OP. P should be the end point of the resultant. So here is our resultant FPO. The tail of the resultant is O and the head is P. So we have successfully added both these vectors. So depending on the point which you have in the vector polygon, tail or head, first of all you have to identify whether the available point with you in the vector polygon is the tail of vector or the head of vector. Accordingly you will place the vectors. So what is the scope of this lecture? We have not gone into any mathematical derivations or proof of all the vector quantities of circular motion. We have just revised the things which we should know before starting the relative velocity and acceleration analysis method. So construction of velocity and acceleration polygons in relative velocity and acceleration method of graphical analysis of planar mechanisms require whatever things we have seen in today's lecture. Thank you.